This conference will now be recorded.
Hello, everybody. Jordan Girth here with the National Weather Service Office of Observations. Thank you so much for joining us for the Satellite Book Club Seminar Series. This is session number 165. The title of today's presentation is the November 5th and 6th, 2022 Severe Mountain Wave Turbulence Event through the Colorado Rockies. I'm pleased to have Perry Daney and Kevin Sullivan, meteorologists at the Aviation Weather Center, with us for this presentation, and Rick Winther, the meteorologist in charge at the CWSU in Leesburg, Virginia, to facilitate the discussion following. Just a few reminders. As you heard, the session is being recorded and there will be an opportunity for Q&A after the presentation. If you have not signed in with your full name, please note that in the chat and we will address questions asked in the chat in the order that they are asked. We're always looking for future presenters. Please get in touch with Kashad Bowman and Emily Maddox if you would like to present as part of the Satellite Book Club. And perhaps you have a presentation from a recent National Weather Association meeting or the upcoming AMS meeting that you'd like to gain further exposure. The training team can help create training materials that may be unavailable or you may be unaware of. Ross Van Til can help with that. I'd like to thank our TowerS team, particularly Kashad and Emily, who work tirelessly every week to get this off the ground. Lee Byerly, the Office of the Chief Learning Officer, the GOES-R JPSS program, our presenter, facilitator, and all of you for being with us today. Without further ado, let me introduce Perry and Kevin, starting first with Perry, who prior to coming to the Aviation Weather Center spent 9 years in NWS Alaska region at the Weather Service office in Kodiak, WFO Anchorage, and the Alaska Aviation Weather Unit. Since coming to the AWC in 2019, he has continued to make a difference with the theme of passing along knowledge to other forecasters and has assisted fellow coworkers presenting on severe turbulence events. He has established the quarterly collaboration meeting with the Western and Central CWSUs, as well as the Alaska Aviation Weather Unit, Honolulu Forecast Office, and the Anchorage CWSU, where they highlight severe turbulence events. Before joining NWS, Perry worked as an observer at George Air Force Base, California, and Plattsburgh Air Force Base, New York. While enlisted in the U.S. Air Force, he has a bachelor's from State University of Oneonta, New York. And Kevin has been at the Aviation Weather Center for 2.5 years. Prior to that time, he spent 10 years in Jackson, Kentucky, and 6 years in Gaylord at the Weather Forecast Office there. Kevin graduated with a bachelor's in meteorology from Iowa State University. So we're glad to have both of their expertise with us today. Looking forward to their presentation. Perry and Kevin, welcome to the book club.
Thank you for having us.
Yes, thank you.
So we're going to be covering a severe turbulence event that happened due to a mountain wave on November 5th to 6th, 2022. We tend to get a lot more mountain waves activity in the winter time, so it's not surprising this was a November event. We're kind of heading into that cold season right now, so we're going to be seeing a lot more mountain wave events as we get into the winter season. So figured this was a good time to bring up turbulence. So Perry and Ryan Connolly, who also worked and Emily Nubar, who also works at the AWC, all helped put together this presentation. So it was a collaborative approach to this presentation, and appreciate all their help. So we're going to start with kind of look at the outline of kind of what we're going to talk about today. We're going to kind of look at the atmospheric pattern that kind of led up to this event. Then we're going to look at some key features that led up to this event as well. We're going to kind of use a mountain wave induced turbulence decision tree that's been developed by a number of people here at AWC to kind of help us give an idea of when we need to issue a SIGMET for severe turbulence. So we're going to kind of take you through that decision tree as we work through this presentation today. So and then finally we'll conclude with a summary of the event. So to begin, we're going to start with this top-down approach. We'll start at 250 millibars and kind of look at the setup with the jet that day on November 5th. This event was mainly on November 5th. It went over 0Z into the 6th. So it was mainly a late afternoon, evening event across the Colorado Rockies. Thing to note, this event actually started up in Wyoming. We got a number of severe turbulence reports aloft over Wyoming earlier in the day and prior in the day over Wyoming. So the Tetons was very active as well with this event, but eventually translated down into the Colorado Rockies. So what's interesting to note on this event is that we had a nice 250 jet pointed right into the Wyoming area at 0Z on the 6th. And that put Colorado right in the right front region of that jet coming into the Colorado area. So, and I'll talk about that here in a little bit, why that was important. It's part of our decision tree. It's kind of an ideal location to be if you want those mountain waves to be induced. So looking at 500 millibars, we had a kind of a shortwave trough kind of moving through the region, extending from Colorado or the southern Canadian provinces down southward into the Rockies. So we had a nice little shortwave trough moving through. That's the main feature on the 500 millibars. And at the surface, we had a low pressure system in the southern Canadian provinces with a cold front stretching down into the kind of the northern Rockies. And Colorado remains out ahead of that cold front presently, so at 0Z there. So 0Z is kind of when the height of this event was taking place, 21 to 0Z roughly, so I used the 0Z analysis
Will now be recorded.
kind of give a summary of this event. So looking at our decision tree, this is kind of our decision tree that I'm going to take you through. So basically, if you meet the criteria, we go on to the next step. If you meet the criteria, you keep going down until you get to the point where you're going to issue a SIGMET, which is equivalent to a warning for aviation weather. So, so this is kind of getting us an idea of whether or not we need to issue a SIGMET or not. So, if we don't meet any of these conditions, then we won't issue a SIGMET. So, again, this decision tree has been produced over the years by a number of forecasters here at AWC. So, we find it very handy, and a lot of these things are very critical to getting mountain waves. And mountain wave forecasting has always been difficult. Sometimes conditions look ideal, and you don't end up with a mountain wave, and you don't end up with any reports. Sometimes it's more marginal, and you do end up with a lot of reports. So, but we found that using this flow chart kind of gives you the idea that we have a pretty good chance we'll see some a report or get some severe turbulence if you meet all these conditions. So the first one that we kind of look at is, do we have perpendicular cross barrier flow with wind speeds 35 knots or greater, or do you have ridge top wind speeds of 50 knots or greater? So generally speaking, when you get these kind of conditions to form, you're probably going to have low level chirp. You're probably going to have in the low levels, generally below from the mountaintop downward down to the surface. You're probably going to have severe turbulence in the low levels. However, this is also a key contributor to getting a mountain wave to form as well. So that's the first thing that we're going to kind of look at today. So looking at the RAP 600 millibar winds, on the left here is the 21Z, and on the right is the 0Z. You can see that we have 50 knot winds through the Colorado Rockies. So it basically is from west to east. So you're talking about cross barrier flow in the Colorado Rockies. That's pretty good cross barrier flow across the Rockies. So so we did have a low level SIGMET already issued at this time because of course we had that good low level flow. So so we're already probably getting some severe chirp in the low levels. But we're kind of concerned about higher up towards the tropopause. Are we going to get severe turbulence high up in the atmosphere? So we had the strong cross barrier flow. Here's 3Z and 6Z. You see that strong cross barrier flow continued right into the night. It continued pretty good. In fact, it actually picked up a little bit as we went into the overnight hours. But as I'm going to show a little bit later, the mountain wave didn't continue in the overnight hours, even despite the fact that we had this strong cross barrier flow. It actually weakened a little bit. So I'll explain that here in a little bit why that happened. And then we're looking at the RAP 1800 to 2700 foot above ground level winds. This is from 21Z to 6Z. You see that again, you see those reds in there. That's 50 knots or greater of wind speed through that region. So you're certainly getting that strong cross barrier flow that you need for this event. So the next thing that we're going to look at in our decision tree is, does the satellite show a phone gap or subsidence or any severe turbulence pilot reports? So while it's not ideal, we don't necessarily want to wait for pilot reports to come in before we issue a segment. We would like to get the warning out before it develops. So mainly we're looking at the foam gap. Do we have that foam gap showing up on satellite? So looking at the satellite loop, this is the 6.9 micrometer channel. It's the kind of the water vapor channel off the GOES-R, or GOES satellites, I guess. You can see that, in fact, we do have some drying noted in both these circles here. The yellow circles indicative of that foam gap developing here. You also notice that there's standing clouds. The clouds really aren't moving a lot off the mountains. That's another good indicator that you got something going on there. So while we have this foam gap developing, you can see that the clouds also are not moving off the ridges as well. They're in the Colorado Rockies. And then looking at the GOES 16 RGB air mass channel. So this is a nice channel. It really does show. It's really easier to pick out turbulence when you're using the RGBs. Kind of highlights the areas that you're concerned about. So, and you can see it back here in Nevada. You can see there's actually some scallop clouds. That's a good indicator of turbulence. But this is actually a trap wave. This is actually probably more like low-level turbulence that's affecting this Nevada area. Because you don't see the foam gap, you also don't see the standing clouds. So you're probably not seeing mountain wave activity back here in Nevada. But if you look over here in Colorado, you do see the standing clouds, and you do see the foam gap, the drying that's taking place between the clouds here. So that's indicative of that you probably have some good turbulence developing aloft in the atmosphere. So that's kind of what we're looking for, one of our key contributors, and we were looking at satellite data. So in fact, we did have pilot reports. I don't necessarily like to show these this early in our decision tree, but we decided to go ahead and show them in this step, and to show that we did actually have some pilot reports. The ones that are in green here are actually low-level turbulence reports, so basically below 18,000 feet. And the ones in yellow are generally above 18,000 feet. But if you look at our reports, we actually had the first report here is flight level 38,000. So this is 38,000 feet was this first report. Then this next report was 43,000 feet. And this next report was again 38,000 feet. So generally speaking, our reports were very high up, 38,000 to 43,000 feet up in the atmosphere. So and the bottom one here was actually from a Boeing 789. So that's a big plane. And we tend to take more notice when it's a big plane reporting severe turbulence, because it takes a lot more turbulence to rock the big planes around. So the fact that we got and this was early on, this was 1930Z. So we got this report very early on in the day of this severe turbulence. And then these other reports came in closer to 0Z that day. But these are smaller planes, but again, still causing problems with the aviation community. So those are the reports that we got that day. So of course, yeah, we're getting reports. This Boeing 789 obviously gave us red alerts. Like, we got to get something going and got to get a segment out. So the next thing we're going to look at is the 300 millibar jet right front exit quad, or left rear entrance quad. For this one, we were actually in the right front exit quad. This is the one that we were talking about. We were looking at 250 millibars earlier. So, and here's a loop from the RAP 300 millibar winds from 21Z to 6Z. And you can see that we have that we're pretty much in an ideal location. We're right in that right exit front region of that jet at 300 millibars. So, and the reason that we were looking at that area of the jet is because we want an area that's going to have weak shear, but you're also going to have some instability. Because if you have too strong of a shear, it's going to rip apart the updraft, downdraft couplet that we need to get the mountain wave to form. So we're really looking for an area of weaker shear to form so that you can get that mountain wave to form. So that's kind of why we're looking at that right exit region of the jet. So, okay. And also we have a tool that we use at AWC. It's called the Graphical Turbulence Guidance, and it's called GTG for short. Over here on the left is from flight level 3,000 up to 34,000. So this isn't quite up to where we were getting those severe turbulence reports. But you can see that we're not getting a lot of the brighter colors on this product. We're really looking for areas that are red or even pink that are showing up that really highlight those areas of severe turbulence. So right there, it's showing that there's probably not a very good layer in there, in that layer. But if you look up on the right here, from 34,000 up to about 39,000 feet, you're starting to see some of those reds and yellows and oranges show up. That's indicative that product, it takes into account a number of different things from the different computer model outputs to generate a turbulence forecast. And obviously it's picking up on some stuff that it's saying there's potential that there is severe turbulence happening there. But you do notice that it does drop off towards the end. It does drop off a little bit towards the end of this loop here. So the best conditions were probably early on in this loop from about 21Z to about 3Z roughly. And looking higher up at about from 39,000 feet up to about 45,000 feet, you see the colors even get brighter. I mean, we even get some pinks that show up in here, showing up in the Colorado Rockies. So definitely clues us in. Hey, there's probably something going on here. I'm taking you through this a lot slower than we probably would in real time, but we probably would already be like, okay, let's get this thing drawn up and get it ready to go. So, generally speaking, we had some good potential for turbulence aloft with this event. So the next thing we're going to look for is inversion near the mountaintop. And generally speaking, we like to use a 1.6 rule when it comes to wind speeds between the mountaintop and about 2,000 feet above the mountaintop. If the wind speeds are more than the 1.6 rule, then you generally are probably not going to see a mountain wave. We really want the wind speeds to not differ that much going up above the 2,000 foot layer. So you really want the values less than the 1.6 rule. This allows your vertical propagating couplet to develop in that stable region. So you really need that stable layer to develop right about the mountaintop area. So for the Colorado Rockies, we're looking at about 600 millibars as an proxy for the ridge top. So, and then we're also looking for lapse rates that are low. We don't want too much instability to form within that mountaintop region. So I'm going to show you some soundings here. This is starting off at 21Z. This is from Eagle, Colorado, which is plotted here on this map. You can see where it's plotted there. And looking at 21Z, you see there's a pretty strong inversion right about 600 millibars. Pretty strong inversion. And you're looking at the wind speeds here. You see that we're generally about 45 knots going to about 50 knots. So there's not a lot of wind shear here. Or wind speed change. So you're probably looking at a pretty good setup for mountain wave because you have that inversion. It's a bit stable, and that allows that propagating wave to move upwards in the atmosphere. So you don't have anything that's going to kind of tear that apart and break it up. So and then looking at your lapse rates over here at we didn't have 600 to 500 millibar lapse rates available to us at the time we put this together, but we had 700 to 500, and so we use that as a proxy for what we need to use it for. So and you can see that the six line is way up here north in Wyoming, in Nebraska, and so that we can assume that lapse rates are pretty low across Colorado, and so that's pretty good assumption that our lapse rates are within our acceptable range to get mountain wave to form. So, and moving on along to 0Z, you can see that at 0Z, that inversion that was at the mountaintop is starting to weaken just a tad. It's still there, but it's starting to weaken. You see the wind speeds are starting to pick up as you go up higher up off the ground there. So, so your wind speeds are starting to increase. Your lapse rates over here on the 700 to 500 millibar lapse rates are starting to drop southward towards Eagle, Colorado. So that's indicative that the mountain wave event may be starting to fade, but it's still ongoing because you still got that inversion, and you don't quite get that 1.6 rule with the winds. So so it's still acceptable and still ongoing, but by 3Z, you look at the mountaintop where the inversion was before, and it's now gone. It's completely eroded. In fact, the wind speeds have really increased. It goes from 30 knots almost up to 60, 70, let's say almost 80 knots there. So the wind speeds have really increased. And you look at the lapse rates over here on the right, and you see that 6th line is going right through Eagle, Colorado. So you're getting to the point where it's no longer acceptable. You're not getting that stable layer at the mountaintop, and thus your mountain wave event's probably coming to an end. But you're probably still dealing with low-level chirp because the low-level winds across the mountaintop are still pretty decent. So you're probably still getting some low-level chirp, but you're probably just not getting that higher-level chirp. So the next thing we're going to look at is, do we have a sharp or strong updraft, downdraft couplet? And does this strong vertical propagating motion or couplet punch through the tropopause? So this is kind of our last step here. Kind of look to see. We look at a cross section. This cross section actually was drawn backwards. So if you look at the cross section, it's actually backwards of how you might want to draw it. Over here on the right is actually Grand Junction, Colorado, and on the left is Lyman, Oklahoma. So the cross section actually goes from east to west, not from west to east, like most people draw them. So, but for the purpose of this presentation, it shows what we need to show. So we opted not to redraw it and redo it. But first off, the first thing I like to point out is where the tropopause is, because that's what we're concerned about when we're forecasting mountain waves. Because generally speaking, we forecast mountain waves, we generally look for about 5,000 feet, or no, 4,000 feet above the tropopause as the top of the turbulence layer, and about 5,000 feet below the tropopause. So we're looking at about a 9,000 foot layer that we're kind of looking at for potential severe turbulence. And you can see here that our turbulence, our tropopause is about 38,000 feet. So that's where our tropopause is located, about 38,000 feet. And you can see that we have a strong upward and downward couplet here. And you can also almost see a possible hydraulic lift here within the potential vorticity lines here. And so this is a pretty good indication that, hey, this couplet is actually punching right through your tropopause. So when you see that punching through that tropopause like that, that's indicative to us that, hey, there's a mountain wave event ongoing with that at that time of whatever you're looking at. So Perry, did you want to explain this loop here?
Sure, Kevin. Hi, everybody. This is Perry Danny, lead aviation meteorologist here at AWC. I wanted to thank Emily Nyberg for this cross section. It's a WRF 3-kilometer loop from 4Z on the 5th, and it goes through 11Z on November 6th. With that, she put on the wind speeds, which is the colored or the image that's colored, and then the potential temperatures. And with that, your units on the left there, you'll see wind speeds, meters per second. That should have been over here with this column. That's what this refers to. But the other numbers here are the meters, the height. So and I put them. I did a rough translation into 4,000 meters is roughly 13,000 feet. 8 is roughly 26, and then up here, the numbers spitting out there's 12,000 meters, so roughly 39. But with that, I captured. I put with this. We're looking the higher resolution. This is all post analysis. We can do the NAM 12-kilometer or the RAP 13-kilometer, and that's really good for showing the couplet, which you'll need that vertical propagating couplet, and then you look for the key. Is it punching through the trope? Because that's excellent indicator where we're going to have the turb. So, but with this, this would really help would really help us even more in the future to be more proactive and as always safety for the aviation community. So with us, you can see it'll give us more confidence that, hey, we have a breaking wave. You can see it'll when it jumps down. When it jumps down, looks like a check mark, like I'm showing here, and it goes all the way up through the atmosphere. I'm trying to find the time. The time's right up here. Sorry about it's 5th, right around 21Z to 3Z. That's when things really punched out. Here we go. That's 6, 7. Look, it's starting to form. And this is the Eagle area and then Denver area, and then 22Z. Look at that, both areas. So I'm not positive if this mountain wave affected both areas. If it started in Eagle, because you're going from west to east, and then it moved over to Denver, that area. So, but with this, the key thing is that you can see you have a breaking wave. It's breaking. That hydraulic jump is going from the ridge tops all the way up through, and that wave propagated all the way through the tropopause. So that's really, again, the key feature, that just another tool to reinforce us to be proactive and issue that segment, and don't ride the fence. But that's really our theme is safety again. And if everything lines up, our dynamics back us up. We don't want to be the boy that cried wolf, but we want to be proactive and not wait for all kinds of severe turb pilots to come in, but to be if we can to get that warning out as fast as possible. But I'll pass it back to you, Kevin, to wrap it up.
Okay.
Thank you.
Thanks, Barry. Yeah, it'd be nice if we could get these kind of products in real time, but unfortunately this was made after the fact, and we can't get this kind of resolution in real time. So, but it would certainly aid in our decision process if we had this in real time, but unfortunately we don't. But so yeah, so anyway, so we get to our last step, and we've met all the criteria, and we continue to say yes on all of these. So we issue the low or high level SIGMET, and here is the SIGMET that we actually ended up issuing. This was actually issued at 2015Z that day. And all our SIGMETs last for about 4 hours. So so this one goes to 15Z. I imagine there might have been one issued after this. I'm not 100% sure on that. So, but this is kind of the SIGMET that we ended up drawing up that day. So again, this didn't go all the way over to Denver. Maybe it should have gone over to Denver. It looked like maybe the event might have moved over that Denver based on what Perry showed you in that loop. So the next issuance after this might have included Denver, gone over that direction. So anyway, as a summary for this event, we had that strong cross barrier flow across the Rocky Mountains. We were in the right front exit quad of the jet, which again provided the low shear and the good instability to get that couplet to form and to help it punch through that tropopause. The 300 millibar jet winds showed a strong northwesterly to westerly jet core, intensified by 18Z on the right front exit quad, then entered the western to southeast Wyoming and Colorado regions. So that really helped keep Colorado in that right exit quad. So the NAM cross sections through Colorado showed a vertically propagating wave punching through the tropopause, around 250 millibars. We had 700 to 500 millibar lapse rates that were four or less, that coincided with aiding and developing of that vertically propagating couplet. And then that WRF 3 kilometer cross section clearly displayed the hydraulic jump in the breaking wave that broke through that tropopause. So it really enhanced that. If we had that in real time, of course, that would enhance our decision making with going with a SIGMET. So some future things to kind of consider is how to better analyze and understand cross sections of propagating waves, and using the 600 to 500 millibar lapse rates and QG forcing, which I don't believe we have that in AWIPS right now, but I think we're going to be getting that here pretty quick here at AWC, and hopefully we can start looking at using that a little bit more as well. So I guess that brings us to the end of our presentation.
All right, Rick Winther here. Can you hear me all right?
Yeah, yep.
Yeah, so I'll be your facilitator here. Great presentation, Perry and Kevin. That was an excellent case study on turbulence, mountain wave turbulence. A few announcements here before we get into the questions and discussion. I'd like to encourage all attendees to stay on for questions and discussions. You can post your questions in the chat room and we'll field them through there. Sign in with your full name when asking a question. Also, it would be great if you could complete the feedback survey that will be posted in the chat room. And in addition, in a week from today, on Thursday, October 26th at 12 p.m. Eastern Daylight Time, Arunas Kousakis, I'm sorry, Arunas, if I got that wrong, and David Peterson will discuss the prediction of pyrocumulonimbus events through the remote sensing resources. And I also like to encourage attendees to contact the Tower S team, Kashad Bowman and Emily Maddox, for questions about the SBC for configuration of satellite products. So let's get into discussion and questions here. Again, you can post your questions in the chat room. We've already got a few comments and questions. We'll start up top here with Brian Curran. For mountain waves across the Guadalupe Mountains, we've used jet normal ageostrophic wind streamlines to assess turbulence and gusty severe winds at the surface. That's interesting, very interesting. Perry or Steve, did you want to comment on that?
Yes, that's I always encourage the other people. Oh, I could put my camera on. Sorry. There you go. Sorry about that, folks. I totally forgot. I was so focused on unmuting. Anyway, yes, this is a team effort. Everything that I've learned through since through Alaska to here now, it's all been me asking questions and what works best. What have you, the different people at the CWSUs, what have you found that works really well? Because you know your area way better than the other folks who just don't work that area as much. But yeah, I've been using also the Sioux Paul Slater as well with this through the Denver region as well. I'm not familiar enough with the ageostrophic winds with the low level stuff. I use the RAP a lot, so I probably didn't help you much, but I'm just thinking, because we're looking at that decision tree. If we like to see 35 knots at the surface, just because it'll accelerate up the mountain ridge, and then hopefully it'll be stronger aloft then, at the top. So, but if that's something that can really help to aid to help us to have more confidence in putting out something, if we're going to have something, I'm all for it. So if you can help me to learn that better, I deeply appreciate it. I didn't really answer your question, but that's what was going through my brain at the time. Sorry.
Very good, very good. Yeah, I had one question. So you were talking about the right exit front jet. You want that very weak shear. And of course, in shear, you can either get directional shear or speed shear. Is there any of those two shears? Is there any one that's more mitigating than the other?
I think they're both about the same. We're really the whole point is if it's too strong a shear, it just rips that couplet apart and it'll tear it apart, and that's what typically will happen. Will happen. So and also you typically will see with mountain waves that I've seen here recently as well. It was nice to see it firsthand instead of reading about it, but you get a stronger inversion that develops, let's say like at 500 millibars, and then that caps it off, and it doesn't allow the wave to propagate anymore, and then we start losing that weaker shear, that layer, 100 millibar layer, that's above, like from the ridge top and above. So that's what Kevin was showing there when he was going through the slides there, and why it started diminishing, because we lost that favorable stable area. So I hope that helped.
Yeah, excellent, excellent. So moving on here, Scott Lindstrom had a comment and a question here. 21Z is a good time for a NOAA 20 overpass over Colorado. New caps from NOAA 20 can give useful mid-level 500, 600 millibar lapse rates. Do you use those satellite data to validate what you're seeing in the model? I'll throw it out to either Perry or Kevin.
Yeah. I mean, that's a good point. That is a favorable time for around that time that we get the new cap stuff. So that could certainly be useful. I haven't used it much operationally, but certainly something I might consider doing in the future, knowing that. So I appreciate that input. Perry, you have anything you want to add?
Just the same thing. A lot of times when what happens a lot is we have with the greater dynamic systems, it's just we wind up chasing our tail so much where we don't have time to look at everything, and that's one of the I know other forecasters that's like grilled into them. They'll look at those, and I know one of the things I always look at is kind of getting off the trail, but is looking back, looking at the satellite. Hey, do you have those indices? Do you have that phone gap? Do you have those standing clouds? So stuff like that. But yeah, I'm that's one of the things my goals this year is to incorporate what you just mentioned more, because that's and using ACAR soundings. I think I'm butchering that, but ACARS, those as well, because you can get real-time pilot reports through that real-time soundings, I should say. But yes, that's a great point. I just want to let you. I guess my point is that sometimes we get so wrapped up and so focused on other things that we miss the other things that would really help us to validate things and give us more confidence, because again, we don't want to be the person, crying wolf. You go, oh yeah, there's another false alarm, but we don't want that. We want to be, so the people are going, yeah, they're putting out a warning. It's likely going to happen because we're not just putting them out because, okay, we want to, cover our tails. You know what I'm saying? Thank you.
Excellent, great. Yes, Scott Lindstrom had another comment, and you must have noticed I posted a link at the top of chat that talks about the CMIS turbulence probability tool using AI technology. But he goes on to say there's the machine learning based tool out there. It gives information on the probability of turbulence given current satellite and model data. And he goes on to ask, was CMIS turbulence probability being used on this day to add confidence to your decision to issue a SIGMET? So I know the tool, the page that I posted at top, I think that tool just covers above flight level 3000. But Anthony Wimmers, who's working on that, may be progressing in that low level turbulence. But I don't know if you want to comment on that.
I'm pretty sure. I worked the first part of this event, like the previous day going into as this event dropped down through like Kevin was saying, through Montana, then went through Wyoming, and it was on its way to Denver. I'm pretty sure we didn't use that that day. We had enough other things that that through that decision tree that we felt pretty confident, and then also that upstream it had been producing mountain wave severe turb reports, so we felt pretty confident in that. But again, that's another great point, another one to remember, not to remember, but to incorporate that in there. That's one of the things that too that another co-worker mentioned to also incorporate doing cross sections with potential vorticity, because that will help you to see a better another tool in a C to help you see where the tropopause is, because that's really the key with that couplet. As it punches through, if it's strong enough, that's where your severe turb is going to be. And if you can get that layer down where that tropopause is, instead of as well using the cross section with the NAM12 and RAP 13, it'll just help. So it's just good things that I'm adding to my list. Believe me, because I want to get better, as well as Kevin, get better at forecasting mountain wave events.
Very good, very good. Yeah, we're getting near the end here, so we have one more comment. Adding to Scott's great comment, Nesdes is beginning plans to transition this product into operations. So yeah, that's that AI tool that they're talking about. Just one last comment. I mean, it's tough because you guys are sitting there at the desk and you don't know, everything looks like it may push some severe turbulence out, given the right, mountain wave barrier winds and stability. But if you issue that SIGMET, then you have a good chance that there will be no aircraft flying through that area. So, I mean, how often do you wait for that first report, or do you just go with it?
I push not riding the fence if your dynamics are really good, and they're not overdoing it, and that's getting to know your product more and the different pattern recognition. But if we have those different points from the decision tree, and that really helps to give is giving me a greater confidence, and then going back and doing these case studies. Kevin and I will continue to do this, but that's what really helped to reinforce, because you wind up digging in more and say, oh, look, I missed this, or look at this. This is why we had an inversion set up at 500 millibars at a previous one that was up in the northern Rockies in Montana that lasted 3-4 hours. I found out, well, it's because there's a 500 millibar inversion that's set up, and it only lasts 3-4 hours. So again, it's safety. That's our key point. If we're confident in it, I prefer not. I really push not to ride the fence, to issue it for safety. But again, it's a fine line. You can't just go have a boatload of false alarms, because then that does no good. So so it's kind of trying to find the happy medium, and the more confidence we have in the different events. And again, I can't stress enough case studies and other people. It's a team effort with the other forecast offices to help one another, because this is not all me or Kevin. It's other people that's helped us to get here and be better forecasters. And that's a theme with the collaboration meetings, is passing along knowledge to other forecasters, because again, as you know, a lot of people are retiring, and then the new ones come in. So it's a learning curve, and it takes a couple of years before we feel well, at least I felt confident in forecasting, because you got to learn pattern recognition, and then what's what. So it's a learning curve. Thank you.
All right. Well, again, thank you, Perry and Kevin. That was a great talk. I'll pass it on to Jordan.
Well, thank you so much, Rick, and I really appreciate the great presentation, Perry and Kevin. Always great to get some exposure to different aspects of the National Weather Service mission. As has already been mentioned, we're going to continue the Satellite Book Club next week, Thursday, October 28th, 12 noon Eastern Time. Arunas Kusiauskas and David Peterson are going to be talking about pyrocumulus events. And in the meantime, if you need to get in touch with the Tower S team, whether that is with regards to the Satellite Book Club or the configuration of satellite products, Rashad Bowman and Emily Maddox can help you with that. Also, find us on the NWS internal Slack. Tower S channel. So please get in touch with us there. In the meantime, I hope everybody's having a great fall, and we'll see you again next week. Take care, everybody, and thanks so much.
Thank you.